In this video, we're going to go over a complete breakdown of stoichiometry. Stoichiometry is a branch in chemistry that deals with the relationships between the reactants and the products, as well as doing conversions between them. So if we look at this first example, we have 2H2 plus O2 yields 2H2O. If they ask us how many moles of water are produced with 3 moles of O2, let's see how we can do this conversion. First, let's make sure that our equation's balanced. We have 4 hydrogen atoms on the left, 4 hydrogen atoms on the right. We have 2 oxygen atoms on the left, 2 oxygen atoms on the right. So this is a balanced chemical equation. So if they give us 3 moles of O2, we want to figure out what this number is in terms of H2O. Meaning we're going to have to convert our units. Our units are in moles of oxygen. We want it to be in moles of water. So we need to come up with a conversion factor to kind of bridge the gap between the oxygen and the water. If we look at our balanced chemical equation, we know that for every 1 mole of our oxygen gas, we will get 2 moles of water. So we can use this ratio as our conversion factor. So if we multiply this by that ratio with 1 mole of O2 on the bottom and 2 moles of H2O on the top, we'll end up canceling our moles of oxygen. Since we have 1 on the top, 1 on the bottom, we can cancel them out. All we're left with are moles of H2O. Now when we do this math, we're going to end up with 3 times 2, which is 6, with our unit, moles of water. Let's take this a step further. What if they asked us how many moles of water we can make with 47 grams of oxygen gas? So in our last example, we were looking at a mole to mole conversion, but now we're working with grams of oxygen gas. Now we have to think, is there a way to get from grams of oxygen to moles of water? There isn't any ratio that we can use, but we know there's a ratio to convert from moles of oxygen to moles of water. And we know that there is a ratio to get from grams of oxygen to moles of oxygen. So this is just going to be a multi-step conversion equation. So if we start with our grams, we can use the molar mass, which is grams per mole as the unit, to convert from grams to moles. So for oxygen gas specifically, it's roughly 32 grams per mole. So we want our grams to cancel out, so we're going to put 32 grams on the bottom and 1 mole on the top. The reason we did this, again, cancel out our grams of oxygen. But now we're in moles of oxygen, and we want to be in moles of H2O. Well, we can use that conversion factor that we saw in the last example and convert our 1 mole of oxygen gas to our 2 moles of H2O. Now what we did here was cancel out our moles of oxygen, and our only unit left is our moles of H2O, which is what we want our answer to be in. Now we would just solve this algebraically. 47 times 1 over 32 times 2 over 1. That gives us roughly 2.9 moles of H2O. Let's look at a new equation. We have CH4 methane plus 2O2 yields CO2 and 2H2O. This is the combustion of methane. So if they ask us how many grams of CO2 can we produce with 4 moles of methane, CH4, how can we go about solving that? So we're going from moles of CH4 to an unknown amount of grams of CO2. So this is a mole to gram conversion. So if you remember, to get from moles to grams, we can use the molar mass. But we have moles of methane and grams of carbon dioxide. We can't do our molar mass conversion. We have to first do a mole to mole conversion. And it'll look like this. We start with our 4 moles of our CH4. We have to figure out how to cancel this out. Well, we know, according to our equation, that 1 mole of CH4 gives us 1 mole of CO2. It's a 1-to-1 ratio. So if we explicitly write this out, we can write that 1 mole of CH4 on the bottom is the same as saying 1 mole of CO2 on the top. Now the reason moles of CH4 is on the bottom is because in our first term, moles of CH4 is on the top, and we want to cancel this out. So right now we're working with moles of CO2 as our unit. But that's not what they want our answer in. They want grams of CO2. So we can further multiply this now by the molar mass. We want grams, so we're going to have our grams on the top and our moles of CO2 on the bottom. And if we look at the molar mass, for every 1 mole of CO2, that equates to 44 grams. Now what do? We canceled out moles of CO2, leaving us with grams of CO2. Now we just solve going across. We're going to do 4 times 1 over 1, so it doesn't really change, times 44, giving us an answer of 176 grams. Now let's look at how to convert from mass to mass, or from grams to grams. It's asking us how many grams of our aluminum oxide can be produced with 10 grams of aluminum. So we're starting with 10 grams of aluminum. We want to end with a certain amount of grams of aluminum oxide. So we have to go through this entire process of converting units until we find a conversion factor to get to grams of aluminum oxide. Right off the bat, I know if I want to convert from one molecule or one atom to a different molecule or atom, I'm going to use a mole to mole ratio. Right now, I have aluminum in grams. If I get aluminum in moles, I can convert it to moles of any other compound. So I'm starting with 10 grams of aluminum. I'm going to multiply by the molar mass because that's going to get my conversion from grams to moles again. So we're going to do 1 mole on the top equates to roughly 27 grams. Now this cancels out grams of aluminum. Now we're working with moles of aluminum. I want to get from moles of aluminum to moles of aluminum oxide because that's what they want our answer to be in. So I'm going to look at our equation and do a mole to mole ratio. I know moles of aluminum is on the bottom, and moles of aluminum oxide is on the top. But let's look at what those values are actually going to be. I see that on the reactant side, 4 aluminum gives me, on the product side, 2 aluminum oxide. So we can do a 4 to 2 ratio, or we can simplify it to 1/2. Either one works. Now from here, we're canceling out our moles of aluminum. We have moles of aluminum oxide. We want grams of aluminum oxide. Here's where we're going to do our molar mass conversion. Again, just this time it's going to be for aluminum oxide. So I'm going to have my 1 mole of aluminum oxide on the bottom and our grams on the top. So the molar mass of aluminum oxide is going to be about 101.96. So now if we do the math straight across, we're going to have a unit of grams of aluminum oxide, and we're going to do our 10 times 1 over 27 times 2 over 4 times 101.96 over 1, giving us a final answer of 18.9 grams of aluminum oxide. Let's look at a limiting reactant problem. So if we have our same equation that we saw in our very first example, but this time we're given 10 grams of hydrogen and 80 grams of oxygen, how much product can we make? Well, we have to take into consideration multiple things. The first being that we have amounts of 2 of both of our reactants, but one of them is going to run out first. That's called our limiting reactant. When one runs out, our reaction is going to stop because we don't have one of the reactants anymore. So we have to figure out which one of these is the limiting reactant, or which one of these will run out first. Now we can see which one runs out first by figuring out how much this mass of our reactants converts to a certain amount of product and seeing which product is less. That means it's going to run out first. So if we start with our hydrogen, we want to see how many moles of product can we make with this 10 grams of hydrogen. So if we're only given the 10 grams of hydrogen, I'm going to do the mole to mole conversion. So it's going to be 2 grams of hydrogen is 1 mole of hydrogen gas. That's going to cancel out the grams. Now from there, I'm going to do moles of hydrogen gas to moles of water. So this is my mole to mole ratio. So I'm going to put moles of H2 on the bottom and moles of H2O on the top. If I look at my equation, I see it's a 2 to 2 ratio. So I'm going to have 2 on the numerator, 2 on the denominator. Just to simplify my math, I'm going to make it a 1 to 1 ratio because that's the same as a 2 to 2 ratio. Now from there, we cancel out our moles of hydrogen. We're left with moles of H2O. We don't need to convert to mass of H2O just because we're trying to find in amount of product. It doesn't matter what unit it's in, we just want to know how much product we'll make. So when we do this, we'll end up with 10 divided by 2 times 1, or 5 moles of H2O. This is from the 10 grams of H2. Now let's do the same thing, but with our amount, our 80 grams of oxygen gas, and see how much product that makes. If we have 80 grams of oxygen gas, I'm going to run through the exact same process. It's going to be 32 grams of oxygen in 1 mole. That's going to cancel out my grams of O2. From there, I'm going to do the mole to mole ratio again, where it's going to be moles of O2 on the bottom again, so they cancel each other out, gives me moles of H2O on the top. Let's look at what this conversion is. If we look at our equation, it's 1 mole of O2 yields 2 moles of H2O. So I'm going to put a 1 with my O2 and a 2 with my H2O. Now, we found our hydrogen product in moles, so we can just keep the same product for oxygen in moles as well, just so it's easier to compare. Now we're going to do 80 divided by 32 times 2. That's going to be the math, giving us a total of 5 moles of H2O. Now we want to compare how many moles of H2O our 10 grams of hydrogen produced, as well as our 80 grams of oxygen. Well, our hydrogen produced 5 moles, and our oxygen also produced 5 moles. So that means if we have 10 grams of hydrogen and 80 grams of oxygen, both of them will make 5 moles before they run out. So we actually don't have a limiting reactant, or they can both be considered the limiting reactant because they'll run out at the same time. If we were given a different amount, say we were given instead 5 grams of H2, if we were to redo this math, it's 5 divided by 2, which would end up giving us 2.5 moles of H2O. If this were the case instead, now we can compare, since we have different numbers, our hydrogen product is less than our oxygen. So even though our 80 grams of oxygen can make 5 moles theoretically, it's going to stop after 2.5 because then we're going to run out of hydrogen. We're not going to have any more. We can't make the difference. Let's look at a slightly more challenging limiting reactant problem. So this one, we have C3H8 plus O2 yields CO2 and H2O. This is another combustion problem. Here, we're given 52 grams of our C3H8 and 37 grams of our O2. We're going to do the same thing, except now you may have noticed we have 2 products to choose from. So which one should we do? Well, it really doesn't matter. It's not asking us for a certain amount or for a certain product, how much of a certain product is made. We just want to know the limiting reactant. So we can choose either one of these products as long as we keep the same product for both calculations. So I'm going to do the CO2 just because 3 is the smaller number, so the math may be very slightly easier. So I'm going to start with our 52 grams. If I'm given 52 grams of C3H8, I'm first going to have our first conversion factor, which is our molar mass. So C3H8 has a molar mass of about 44 grams in 1 mole. So by putting our grams on the bottom, we can cancel them out. Now we're working with moles. We're going to do our mole to mole ratio to convert to CO2. Looking at the equation, it's 1 mole of C3H8 to 3 moles of CO2. So I'm going to put 1 mole of C3H8 giving 3 moles of CO2. Now my C3H8 cancels out. Now I'm with moles of the product, which is exactly what I want. So I'm essentially going to do 52 divided by 44 times 3 to get my answer of about 3.55 moles of product. Okay, now let's look at our 37 grams of oxygen and see what we get there. If we start with 37 grams of O2, we're going to do our first conversion factor, our molar mass. So it's going to be 32 grams of O2 is 1 mole of O2. Next, we're going to do our mole to mole ratio. So we're going to have moles of O2 on the bottom, moles of CO2 on the top, ensuring that we're using the exact same product. And if we look at our equation, it's 5 O2 to 3 CO2. So I'm going to put a 5 here on the bottom and a 3 here on the top. Now we canceled out our grams of O2 and our moles of O2, leaving us just moles of CO2. So now if we do 37 divided by 32 times 3 over 5, we get roughly 0.694 moles of product. So to recap this, if we're given 52 grams of our C3H8 and 37 grams of O2, theoretically we can make 3.55 moles with just our C3H8, but our oxygen here is going to be our limiting reactant, because after 0.694 moles of product, we're going to run out of oxygen to use and the reaction can't continue. So taking this into account, how much of our C3H8 will we have left over after this reaction? Well, let's see how we can do that. So we know that oxygen, the O2, is going to be our limiting reactant, and that's only going to give us 0.694 moles of CO2, then the reaction stops. But we haven't used all of our C3H8. So what we're going to do is we're going to see how many grams of C3H8 it takes to make this 0.694 moles of CO2. That means that's how much C3H8 is going to be used. When we subtract the difference, we're going to see how much is remaining. So let's go through that. We're starting with 0.694 moles of CO2. Again, we want to get this to grams of C3H8. So we're going to do the same conversion factor, just backwards. So we're going to have 3 moles of CO2, giving us 1 mole of C3H8. Now that canceled out our moles of CO2. Now we're working with moles of C3H8, but we were given grams of C3H8, so it might help to find our answer in grams. So now we're going to use our other conversion factor, our molar mass, and we're going to do 1 mole of C3H8 is approximately 44 grams. So now we cancel out our moles, we're left with grams. Perfect. So now we're going to do 0.694 times 1/3 times 4 over 1, giving us a total of 10.17 grams. So what does this 10.17 grams mean? That means that's how much of our C3H8 we use before our reaction stops because we ran out of oxygen. So if we subtract this amount from our original 52 grams, we will figure out how much we have remaining. So we're going to have 41.83 grams left over when our reaction stops. Lastly, I want to go over one more conversion factor that we didn't get to look at in a previous example. So this is asking us how many molecules are in 0.73 moles of oxygen gas. So here we're going to apply the exact same principle that we have been, where we're trying to figure out a conversion from moles to, in this case, molecules. So if we go back to one of our previous examples and it asks us to find our answer in molecules instead of in moles or instead of in grams, once we get to our moles, we would apply this conversion factor that we're about to go over to get to our molecules as our unit. So if we're trying to convert from moles to molecules, we're going to use Avogadro's number, which is 6.02 times 10 to the 23rd molecules. And again, this is for 1 mole of anything. So if we take that into account, if we take 0.73 moles of O2, we're going to put in our conversion factor 1 mole of O2 on the bottom and our molecule number on the top, which is our 6.02 times 10 to the 23rd molecules, giving us a total of 4.39 times 10 to the 23rd molecules of O2. And again, if we have to incorporate this into a previous example, we just want to get to moles of our desired unit and then do this conversion instead of the molar mass to get to grams.